Hello, everyone. Thank you for being here today. Today, we're going to talk about something that's often invisible, partial discharge, and its precision pinpointing, which is incredibly important for quality assurance in rotating machines and transformers. So, what is partial discharge? Partial discharge is a small, localized breakdown within the insulation. It happens when the electric stress in one small region exceeds the material's ability to withstand it. It doesn't cause a complete failure right away, which makes it even more dangerous because it often goes unnoticed until it's just too late. There are several types of PD. It's generally categorized into internal, surface, and corona PD. Internal PD happens inside voids or air gaps within insulation. Surface PD occurs along the insulation surface. It's especially intensified by contamination or moisture. And corona PD happens in air around conductors when PD is breaking the air insulation. So partial discharge might seem like a small issue, but it's actually a big problem. It wears down insulation gradually and accelerates its aging. It's especially critical in equipment like motors and generators and in transformers. According to IEEE stats, around 40% of all motor winding failures are due to stator insulation issues. And that's why PD detection plays a key role in predictive maintenance. It helps us catch early warning signs before they turn into costly breakdowns. Some of the traditional methods for PD detection and measurement include capacitive couplers, 10 delta testing, and HFCTs. In some cases, the pattern of the discharge can help us identify the type, like internal, surface, or corona. But those methods usually don't tell you where exactly the PD is happening, just that it exists. There are some traditional methods for localization of the partial discharge. First, we have blackout testing, which is done in total darkness on energized equipment. The operator has to wait for at least 15 minutes for their eyes to adjust. This setup is quite cumbersome, as creating a dark room and standing near high voltage components in the dark isn't ideal. Ultrasonic probes or corona probes are another method. They're portable and they pick up the acoustic signals from corona activity. They require very close range scanning next to energized equipment as well. And now let's take a look at how UV technology is used for partial discharge detection. So UV cameras or solar blind UV cameras detect UV emissions from partial discharge in the UVC range. This makes them ideal for outdoor and indoor testing without needing a dark room. Unlike traditional methods, they give you real-time visual image of where the PD is occurring from a safe distance. It's a non-contact, non-destructive tool that's intuitive and field-ready, with results that can be saved or even shared on the spot. Here you can see some real examples of partial discharge occurring on stator end windings found using UV cameras. Those are common areas where electrical stress tends to concentrate. Also, surface contamination, sharp edges, and poor insulation clearance can trigger PD in those areas. This example here is of partial discharge occurring between two phases. This type of discharge typically happens when the gap between phase conductors is insufficient or uneven. In the example here, we can see partial discharge activity detected on coils that are removed from the stator. Common cases of PD on coils include defect in the insulation or insufficient corona grading. Now, partial discharge testing in rotating machines is recommended by many industry standards. For example, IEEE 4034 and IEEE 1799, which provide guidance on the measurement and detection of PD in rotating machines using UV technology. They outline the recommended practices for the test setup and for the interpretation of the results. So how does UV technology help pinpointing partial discharge during different stages of your machine's life cycle? Starting with design optimization. UV imaging is used in prototype testing. It helps to visualize external PD under high voltage stress and to identify weak spots of the insulation. This allows engineers to make design improvements before the product goes into production. Next is manufacturing and quality assurance. So during factory testing, UV cameras are used to make sure that there are no visible signs of surface or corona discharges. This step helps to verify that the insulation quality before the equipment is shipped to the customer. It's a non-contact, fast way to catch issues that might otherwise go unnoticed in a standard electrical test. During commissioning, UV inspection is performed on site to check for PD before a system enters its service. It helps identify issues related to installation, contamination, or transport damage. This stage is also a good opportunity to establish a baseline for the future. So future inspections can be compared to an initial known good condition. In the maintenance phase, UV cameras are used during routine inspections to detect developing partial discharge activity. This supports condition-based maintenance strategies, allowing teams to track changes over time and to intervene before failure occurs. It's especially useful in high-value or critical equipment where unplanned downtime would be especially costly. And finally, in the repair stage, UV imaging helps locate the exact sources of discharge during troubleshooting. After the repair is completed, the same camera can also be used to confirm that the issue has been fully resolved. This ensures that the equipment is PD-free before it goes back into service. reducing the risk of repeating failures. Let's take a look at a case study of how UV technology is used for a PD inspection during periodic maintenance. So we see here they inspected the motor stator that was brought in for a periodic inspection. The laboratory setting is seen here. There is a PD measurement equipment connected using coupling capacitors, and the laptop is connected to display the results. The PD measurement equipment shows that the stator has a PD of over 100 picocoulomb in some of its peaks, but there is no data on the location of where exactly it is located. So this is where the UV cameras are used. And we can see here in this video how the UV camera scans the stator to find exact locations of where the PD is. So we see one spot, we'll continue the scanning. And we find another spot. Now we can fix the insulation in those specific points and verify the fix again with the UV camera. Let's now take a look at where the industry is heading, both in terms of emerging challenges and innovative solutions that are shaping the future of PD detection and insulation reliability. The electric vehicle motor landscape is evolving rapidly, with a major shift towards high voltage platforms, especially 800 volts or more. Those systems support faster charging, reduce the cable weight by enabling thinner wiring, and improve the overall drive performance. They also help manage heat better, which is critical for batteries. And most importantly, they future-proof vehicles for upcoming ultra-fast charging stations that can lead to better operational costs. As EV motors move toward inverter-based designs, they're exposed to fast switching pulses and voltage overshoots. Those high pulses cause uneven voltage distribution across the windings and increase both the thermal and electrical stress on the windings. So this voltage stress, combined with complex geometries and material constraints, together those two factors amplify the voltage stress and increase the risk of PD during normal operation of the motors. In aircraft e-motors, the need for PD-free operation is even more critical. At high altitudes, lower air pressure reduces the breakdown voltage of insulation due to Paschen's law. As pressure drops, the likelihood of electrical discharge increases. So in air, as you can see here in this graph, the breakdown voltage at 10,000 feet is approximately 40% lower than at sea level. So that's why insulation systems must be designed to withstand a partial discharge under those reduced pressure conditions. To address those challenges, UV-based online monitoring offers a practical and scalable solution for continuous PD detection. This system can be integrated directly into production lines, where it performs automated inspections to catch insulation defects during manufacturing and testing. In critical applications, like motors used in nuclear facilities or other critical infrastructure, the UV camera can be permanently installed to provide ongoing condition monitoring of the asset. And since the system detects and logs discharge events automatically, data can be accessed locally or remotely, with alerts triggered when certain thresholds are exceeded. So, to summarize our presentation today, as systems operate at higher voltages, the risk for partial discharge is increasing across many industries like EV motors, aircraft motors, and other critical infrastructure. That's why consistent insulation quality is essential for the reliability of those systems. By pinpointing partial discharge during the machine's different life cycle stages, we can detect discharge early during design and prototype testing. We can perform non-contact quality control during manufacturing. We can perform testing during commissioning to validate proper installation and readiness for service. Online condition monitoring in production lines and in critical applications can be used. And for post-repair verification to confirm PD-free restoration. So thank you all for your time today.